Hello everyone, I'm Bing Xu, a senior undergraduate student and incoming PhD student from Shanghai Jiao University, iPads Lab. Today, I'm honored to share our work, SAFE, software implemented for tolerance for model inference against GPU memory bit flips. Machine learning models are playing a key role in safety-critical scenarios like autonomous driving, financial systems, and satellites. However, edge GPUs running on these devices are much more likely to experience memory bit flips caused by things like temperature changes, unstable voltage, or even space radiation. For example, on some lower-end devices, there can be around 3,900 bit flips happening every day. And for satellites, the number can go as high as 16 million bit flips a day because of cosmic rays. The problem is the model running on these devices are pretty sensitive to bit flips. In fact, research shows that just a 1 bit flip can crash the whole model. When that happens, it can seriously affect the accuracy and the reliability of downstream applications. To sum up, although bit flips happen frequently on GPUs in these safety-critical scenarios, the models running on them are highly sensitive to even a single bit flip. That means protect model reliability on these devices becomes absolutely critical. So the question is, how can we make sure our models stay reliable? Existing approaches can be roughly divided into two categories: hardware solutions and software solutions. One common hardware solution is triple modular redundancy, or TMR. TMR performs redundant computations and takes the majority vote to ensure correctness. While it improves reliability, it also comes with a cost. It requires significantly more computation resources. Another hardware-based approach is to use only reliable memory on the device. But since the amount of reliable memory is usually very limited, this can lead to up to 1,000 times overhead in runtime, which is often impractical. One software-based solution is to use the distribution of neural activations to detect errors. However, this method is highly dataset dependent. It usually requires reprofiling or transfer learning when moving to a new domain. Another approach is to modify the model's activation function and retrain the model to make it more robust to bit flips. But this also comes at a cost. Retraining takes time and resources, and it may hurt the model's performance on the original task. To solve this problem, we have two insights. The first insight is not all hardware bits are created equal. The whole SRAM bits and a small portion of DRAM bits are more reliable. They are less likely to experience bit flips. We can only put critical computation into the reliable memory. The second insight is not all bit flips in software are photo or silent. Some bit flips can only have a minor impact to model result and can be detected. When the numerical changes in the model are less than 1 in a billion, they have no noticeable impact on the model's accuracy. Even when the changes are as large as 1 in 10,000, the effect on correctness is still small, typically less than 4%. This is largely thanks to activation functions like glue, which have a property of interval compression. They map a wide range of input values into a much narrower output range, which means that the model can tolerate a certain level of input error. Specifically, we categorize bits into 3 types. The first type is robust bits. Flipping these bits has only a minor impact on the model's output, A good example would be the ending significant bits of a value. The second type is ranging bits. Flips in these bits can often be detected by checking whether the layer's output falls outside its expected range. The remaining bits are what we call vulnerable bits. Flipping this can lead to significant and sometimes catastrophic changes in the model's behavior. Based on these insights, we propose SAVE, a method designed to mitigate the impact of bit flips on the model. The SAVE workflow consists of 4 key stages: selection, allocation, verification, and edit. In selection stage, we perform static analysis to classify 3 types of bits. The analysis comprises two phases: range analysis and bit attribution analysis. During range analysis, SAVE determines the valid range for each value by propagating ranges through model's computation graph layer by layer. Let's see a concrete example. The initial input range is 0 to 1. The range is propagated to the layer's operator, which performs matrix multiplication. Since the weight matrix is pre-known, SAVE can calculate the relationship between input and output of the operator. Based on the propagated input range, SAVE determines that the output range of operator will be minus 0.75 to minus 0.1. The subsequent ReLU operator, which outputs 0 for negative inputs, allows SAVE to determine that its output is exactly 0. For the final add operator, one input is 0 from ReLU, and the other is the original input, which is 0 to 1, resulting in a final output range to be 0 to 1. Then it comes to bit attribution analysis. Using the ranges calculated in previous phase, SAVE identifies ranging bits and robust bits. For each value, SAVE identifies ranging bits as those must have the same value for all possible values within the valid range. These typically include the sign bit and the exponent bits. For example, if a value falls within minus 0.75 to minus 0.65, then its first 9 bits must be the same. SAVE identifies robust bits as 2 types. The first type is numerical robust. For both upper bound and the lower bound of each range, if flipping a bit in the significant causes a numeric difference less than 10 to the minus 5, it is considered robust. The second type is operator robust. Some operators, particularly activation functions, create additional robust bits. For example, with ReLU and the negative inputs, only the sign bit needs verification and the remaining bits are all robust. Now we have found robust bits and ranging bits. The remaining bits are all vulnerable bits. Next comes the allocation stage. Here, we partition each tensor into multiple blocks based on the proportion of vulnerable bits. Sub-blocks with a higher proportion of vulnerable bits are more likely to be placed in reliable memory, while those with mostly robust or ranging bits are placed in unreliable memory to save resources. In addition, weight tensors are always stored in unreliable memory, since we can verify their correctness by comparing them with a reference copy stored on the CPU side. SAVE also introduces an efficient verification mechanism that offloads most of verification work to the CPU. For model weights, SAVE asynchronously copies weights from GPU memory to CPU after each computation and uses parallel CPU threads to compare with original CPU side copy. For ranging bits, we fuse a lightweight range verification kernel into corresponding computation kernel and uses CPU to check the verification kernel results. For vulnerable bits, we conduct a mixed precision recomputation on CPU. Finally, comes to edit stage. When an error is detected, SAVE simply restarts the inference computation from the fault model layer. We introduce mathematical expectation to show the latency that includes accuracy as a new metric expressed as below. This expression assumes that the second inference is always correct. For correct inferences, which occur with a probability of 1 minus error rate, the time taken is latency, contributing latency plus 1 minus error rate to the total time. For incorrect inferences, which occur with a probability of error rate, the initial inference takes latency time and is considered incorrect. We need an immediate re-inference, so the time for this incorrect inference is 2 plus latency plus error rate. Adding this contribution together, we get the following expression. Thus, we incorporate correctness into the latency. Our end-to-end effectiveness testing showed that our time overhead is less than 9%, with an impact on correctness of less than 1%, and there is no need to modify the model or retrain it. Tests on RTX 4090 indicate that the overhead of our approach is very minimal. We use standard time values here to demonstrate our overhead. The time without any protection is set as 1, while the normalized time for TMR is 3. Both Dr. DNA and RedNight have times exceeding 1.5. Additionally, the robot model cog ACT cannot apply RedNight's protection method. The overhead of our method is only 9%. On the embedded Array platform, our overhead is also less than 9%. The most crucial part of our work is to defense against the bit flips. We tested the ResNet model using real-world bit flip traces from RedNet and demonstrated the fault tolerance of several models. Without protection, the model gets corrupted with just a single bit flip. Using 1-bit ECC, the model can protect against the 1-bit flip, but any flips beyond the ECC's capability also cause corruption. RedNet can tolerate a series of bit flips, but it comes with a decrease in model accuracy. In contrast, our method ensures that the model's correctness with no impact on accuracy even up to 4,000 bit flips in our test. For more detailed testing results, please refer to our paper. In conclusion, we propose SAVE, a lightweight system that improves model inference reliability on GPUs by selectively allocating computations with vulnerable bits to limited reliable memory and asynchronously verification, achieving strong fault tolerance with less than 9% performance overhead. Thanks. Any question?